Hello and welcome to another ANSYS video tutorial. In this tutorial we are going to look at the contact stresses developed between two spur gears. Here's the model that we will use. This is in Discovery. If we open Workbench, we will insert a static structural module. On engineering data, I'm just going to leave that as the default as structural steel. In the geometry, we imported these gears from a website, and you will have access to this geometry file. You can see that these spur gears are relatively thin. That's to keep the mesh size element number relatively small. And we're going to look at the contact stresses that develop between these two gear teeth right here. And we'll talk about the boundary conditions and the meshing and the development of the model. So to begin with, we'll open Mechanical, and I've already created this model, so I'll walk you through the steps that I have gone through. We imported the geometry from Discovery, and you can see that we have two solid parts. We have one part for each gear. They're both made of structural steel, and we've just left the geometry as that. On materials, the only materials we're using are structural steel. And then what we did is we came down and look at our connections. And on connections, we'll go to connections contacts. And what you want to develop here is a frictionless contact between the two teeth. And what you actually want to do is the default here will give you several contact regions. It's best if you go in and modify those regions so that the only contact surface that you have is right between the two gear teeth that are going to be in contact. Now, if you have a model where multiple gear teeth are going to be in contact, then absolutely you'll have more than one face in each one of the contact and target locations. But in this model, we have one tooth that will be in contact with each other, and so we are going to have the contact face be the face that is being pushed in to the target. So in this model here, we're going to set boundary conditions such that this spur gear is fixed and this spur gear is rotating into and compressing against this fixed gear. And so when we come down here on our contact, we want to make sure that we select the frictionless type. We can be symmetric. And then down here on the interface, we want to make sure that we select adjust to touch. So you have several options here for the interface treatment. Make sure you select adjust to touch. And what that does is that sets the two faces in contact at the beginning of the load application. It accounts for any small gaps that may be left due to your geometry model. So if we look at meshing this model, what I did is I came to mesh, and you want to make sure that you have a really good mesh in the area of the contact if you're focusing on the contact stresses. And so you can see that the two gear teeth that are actually in contact are full of elements. And the elements look pretty good in that they're good quads, mainly equal size on each side of the elements. And then as we propagate out into the body of the gears, we have fewer and fewer elements. The way I did this was I went and I created an if you go to mesh and right click, you can insert a sizing. And that's how I inserted these 4 different sizings. And then on the first one, I did an edge sizing. And what I did is I selected these edges here on the first gear. And so if we come up here to geometry and click on geometry and hide this body, we can now come back down to edge sizing, and you can see that the edges that I picked are the edges on the outside of the tooth. I did not select the edges going into the tooth because I don't need the density going into the tooth that I want on these edges. So I selected these 8 edges, and then I came down and I entered an element size of 0.005 inches, and the behavior is soft. Then I went to edge sizing and I picked these horizontal lines, or the lines into the tooth or the gear, and I made the spacing there 0.02, so quite a bit larger. And that gives me a good mesh when I come back up here now and look at the elements just on this particular gear tooth. You can see that I could have made this maybe a little finer, but in general, that's a pretty good mesh for a gear tooth. The other thing that we could have done is in our geometry model, we could have made a face and split the gear tooth off of the body and meshed that body separately. But because I didn't do that in my geometry model, I'm using these edge sizing tools in my gear tooth mesh. These other edge sizing inserts are for the other geometry. So if we come back up to geometry and right click and click on show all bodies, now when we click the edge sizing here, you can see that they're the same edges just on the other tooth. One thing that you want to also make sure of is down here on the overall gear tooth or spur gears, I entered a value of 0.08. And then coming down here, I selected quad dominant instead of prime quad dominant. And I also selected multi-zone instead of sweep. And those settings give me this good mesh right here. If you don't set these, your mesh does not look quite as good as this mesh. Now you can spend a lot of time coming up with a good mesh, but when doing contact stresses, your mesh is very critical, and you want to make sure that you have sufficient elements to represent the changes that occur in a contact stress situation. So those are the settings that we had on our mesh. Now we want to look at the boundary conditions that we need to apply. So if we close our mesh and close our connections, the boundary conditions again that I want to apply are on this gear, I am going to fix it so it can't rotate. On this gear, I am going to put a remote point in the middle, and then I'm going to put on a remote displacement in the middle of this, and I'm also going to apply a moment. And we will talk about those boundary conditions and go through that process now. So the first thing that you want to do is come up to Model and right click and insert remote point. And so you drop down here and click on remote point, and that will insert this remote point right here. If I open up the plus, I can click on that remote point, and what I have done is I have selected one face. And when you select this face, what it will do is it will put the remote point at the center of that face. So I essentially now have a node where I can apply boundary conditions and loads and constraints in the middle of this spur gear. And so that makes it very handy. So I have that remote point there, and it's on this one face. All these other settings here I can leave as the default. Now I can close that remote point, and when I come down here to apply boundary conditions, I'm going to look at a remote displacement. So I'll come up here to supports, click the drop down, and then click on remote displacement. And this will insert this remote displacement right here. And if I click on that, what you will do is on the scoping method, you'll come down and you will have the default will be geometry selection, but we want to click on remote point for the scoping method. So you'll click on remote point and use that as the scoping method. Then down here on remote points, you'll have, if you have multiple remote points, you can name them and you can click on the remote point that you want to use. Since we only have one remote point, we only have one option here, and we will enter that. Now we've identified the remote point that we want, and we can come down here and apply the displacement boundary conditions that we would like to have. And I have entered a 0 in the X, Y, and Z directions and 0 degrees of rotation in the X and Y. And I've left the rotation in the Z direction, which is into the board, into the plane, free. And now with that free boundary condition, it's able to rotate about this axis. Now I can come and apply a load, and so I will come up to loads and I'll click on moment, and it will insert this moment. And on this moment, again, my scoping method will be remote point instead of geometry selection, and my remote point will be the only remote point that I have. So I have now identified the location where I want the moment, and I can come down here and I can say that I'm 0 about the x-axis, 0 about the y-axis, and then on the z-axis I have a minus 1,000 inch-pounds. And that minus will have this gear spin this way with a torque of 1,000 inch-pounds. So that's how you want to set up your loads. My fixed support is simply on the inside of this other spur gear. And so those are the supports that I have set. In analysis settings, I have come in and put on auto time stepping, and I've given the end time of 10,000 seconds, initial substeps of 20, minimum substeps of 20, and maximum substeps of 50. I've also turned on large displacements or large deflection. Even though I probably don't need that in this model, I have it on in case that my load is too big and I can get a converged solution. So now with these settings, I'm ready to go into solution and pick the options that I want to see. I just used the basic ones where I'll look at the total deformation, equivalent stress, and then directional deformations. And then you can go and solve the model. So if we look at our solution and click on equivalent stress, we can see that most of this outside gear is not stressed, but certainly where we have contact, our model shows significant stresses. And if we zoom in here and reposition, you can see that our contact stresses look really good in that we have hot spots on both sides that are in line with each other. They're in line in the contact region, and they're maximum and then decay relatively quickly as we propagate into each tooth. You can also see that we have higher stress concentrations at the root of the tooth, where we will have a larger bending stress due to the contact. So if we zoom in on this, we can come back up to geometry and click on one of the bodies and hide that body, and now come back to equivalent stress and rotate this and see what our stresses look like through the spur gear tooth. And you can see that on these edges is where we get the hottest stresses. And then in the main body, it's not quite as significant. We can also orient this tooth and look at it again in the Z direction, and then create a section plane. Move it more to the center, come up to section plane, and draw a section plane through this tooth, kind of through our hot spot. And now we can rotate this and look at the stresses inside the tooth. And we can actually see that these contact stresses are relatively high inside the tooth down underneath at a given depth. Based on these results, it might be more informative to look at other stresses besides just the equivalent stress. So if we can come back up to solution and go to stress, we can look at some of these other stresses, such as the shear stress. We can look at a maximum principal stress, and we can look at a maximum shear. And now when we click solve here, these new stress parameters will be computed relatively quickly. And if we click on them, we can see what our shear stress looks like through our model. And we can look at our maximum principal stress. And again, here we can see now that this makes a little more sense where we have a high principal stress on the surface, even though our shear stresses are higher down underneath. That matches the theory that we would expect in a contact stress type of model. So looking at these other stress components can be very insightful when looking at contact stresses. So hopefully this has been a helpful video. Appreciate you watching.